Ladies and gentlemen, welcome to the November meeting of the New York Horological Society. Through a quirk of the calendar, it's landed at the end of October. And I want to thank all of you for coming out this evening to hear our special guest, Romain Gauthier, who has come to present for us. Please let me start the meeting. My name is John Tiefert. I'm the Vice President of the New York Horological Society. For those of you in the audience who are guests, please consider joining the Society. If you join this evening, we have membership pins, which are available to you. And for those of you who have joined recently, thank you very much. Many of you are already supporters of Michael Silba's Keeper of Time documentary. I am as well, personally. He is just over 80% of his $100,000 goal. So those of you who have contributed, thank you for that as well. I'm going to consider 25% more than my current level. And for those of you that are contributors, please also make the same consideration. He's quite close, and it is an all or nothing funding. So again, tonight's lecture, without any further ado, the evolution of the chain-and-fusee mechanism in the quest for constant force. By our presenter, please a large round of applause to welcome Romain Gauthier.
Well, I would like to thank you, Nick, and the entire Horological Society of New York for inviting me to speak to you today. I will begin by saying that it's a special honor to be here in the building, the General Society Library, where so many young tradesmen have begun their education. Craftsmen and engineers have been invited here to educate, to inspire for almost 200 years. I hope to add something of value to that history today. Let me also say I am so glad to have the opportunity to address you, the Horological Society of New York, this evening. For me, this is a reminder that when you share knowledge, you keep that knowledge alive. Knowledge that we share with each other is knowledge that we can never lose. And so a group like this teaches, and it preserves, and it protects. It is a reminder of how important is it to educate the next generation of engineers, the next generation of watchmakers. Only by teaching and sharing our knowledge can we take the achievements of the past and use them to inspire new ideas. Watchmaking often moves from looking to the past by creating new solutions to old problems. With that in mind, and I'm going to talk to you about a very old problems for watch and clockmakers, but a problem that has some exciting new solutions. This is the puzzle of constant torque. Today, constant torque is an expectation we have of most machines. Cars and planes, for example, don't start running more slowly as the fuel runs slow. A half tank of fuel doesn't mean half power, just as a full tank doesn't mean full power. The steady supply of energy is independent of the amount of fuel remaining. That is, of course, until you reach the raw fuel remaining. In watchmaking, the fuel is quite different. We use springs instead of combustion and turbojet. Well, most of us do. And springs are the entire reason that constant force, the feat of providing regular and consistent energy to watch or clock movement, has become one of horology's holy grail. When the earliest spring-driven clocks were invented in the 15th century, they brought with them a conundrum that weight-driven clocks did not have. In a clock driven by weights, the weight is unchanging, providing a stable and consistent amount of force as long as the clock is moving around. However, a watch mainspring does not work because of its weight, but because it can be wound, storing elastic potential energy. When a watch mainspring is fully unwound, the spring has no energy accumulated because no coils are wound onto the barrel arbor. This means no stress and no necessity for the mainspring to return to its original state. It is exerting no force. But when you slowly start to wind, the mainspring will start to wind around the barrel arbor and progressively accumulate energy. The more you turn, the more difficult it is to wind. And this is the case until the spring is fully wound and is full of energy. At this point, the mainspring exerts a high level of force. In fact, here, I would like to be more precise in our terminology. Force is a fairly general term, and we would really be speaking about torque, and more precisely, a moment of force, because the torque has a precise point of rotation. But to simplify the concept, and this lecture, let's use the simple words torque. So when we speak about constant force, we are speaking about constant torque. The graph shows the result of a real mainspring torque test as the barrel is gradually turned. It proves the non-linear torque transmitted by the spring barrel from its fully unwound state to its wound state. So here, when we are totally unwound, it has mean zero torque, and until the fully wound position. You have always two lines when we do the test of the mainspring. The one is the torque that you need to wind, and the second curve that you have here is when the spring is going to deliver the torque to the watch. The same is true from its fully wound state to its unwound state. Now, as you can imagine, there is no miracle. The result is a reaction in the balance wheel's amplitude and the movement's timing rate as the mainspring unwinds. In other words, a lack of constant timekeeping precision over the course of the movement power reserve. You can see the effect on this with a simple wind-up toy. When the spring inside a wind-up toy is fully wound, it drives the mechanism with more torque. We saw this on the graph on the mainspring torque curve that I showed you before. As the spring unwinds, it proves less torque to the mechanism, and so the toys slow down. The same is true of the mainspring inside a mechanical timepiece. In watchmaking, we don't want things to slow down. We want to tell a time accurately. And in the 15th centuries, at the dawn of spring-driven clocks, the Verge escapement in use at that time were sensitive to change in torque. This was especially because the hairspring did not come into use until the last 17 centuries. Without a balance spring to regulate the release of energy, the timekeeping of the clock or watch was at the mercy of the particular torque curve of its mainspring. As the mainspring wound down, the balance wheel will oscillate back and forth more slowly. This meant that the first spring-driven clock were less accurate than their weight-driven predecessors. However, the benefits of using springs as a power source were obviously too valuable to abandon. Without springs, we will never have been able to create smaller and more portable timepieces. So, like all good engineers, horologists set out to design mechanical solutions to try to compensate for the variable torque delivered by the mainspring. In Germany, in the 16th and 17th centuries, watchmakers deployed the Stackfreed. This is essentially a long, stiff spring arm that exerts pressure against the mainspring barrel. As the mainspring unwinds, it turns a snail cam, which reduces the amount of compensating pressure provided by the Stackfreed spring. Larger mainsprings were required to power Stackfreed timepieces, and this came with their own larger torque curves. While the Stackfreed did not last, it was nevertheless a creative solution to the puzzle. But for me, this is a rather counterintuitive way of trying to solve the problem. It is a bit like if you ask an athlete to run at the same speed for a period of time because she is naturally very fast at the beginning. You put weights on her at the start to try to slow her down. And then, gradually, you offload the weights. You are solving a problem by creating another one. And it is the case of a mechanical movement. We are introducing friction and wear. A simple yet more enduring mechanism in the Stopwork, the most well-known of which is the Geneva stop, also called the Maltese cross. This is at 17th and 18th century development. So if the problem with the mainspring is that it delivers a higher level of torque when fully wound and a lower level of torque at the end of its state of wind, it's easy to see why a watchmaker will want to prevent the mainspring from ever being fully wound or fully unwound. The Stopwork does just that. By removing the extreme of the mainspring operating range in favor of the more level central parts of its torque. The obvious downside here is that while the delivery of torque is more constant, the total power reserve is reduced. As we can see here, a bit complicated with the light, but normally it was possible to cut that part and to cut, for example, that part. So the only part that was used was the energy from here to down here, but no compensation. It was just to avoid to go to zero. Let's have an understanding. If you see from that point here to that point, we have here 3, 4, 5, 6 turns. Okay, so it has been from 3 turns, we have 1. just to have a look about the first 3 turns, we lose the double. So this is why the Stopwork was used, and why the watchmaker at that time tried to find a way not to compensate, but to avoid the worst part, which is exactly with the first 2-3 turns, because we lose a lot of energy at that side. The Remontoire is another approach to compensate for the mainspring torque curve, but it accomplishes this in a totally different way, to the Stackfreed or Stopwork, and at different places in the movement. The concept for the Remontoire comes from the days of pendulum clocks. The first Remontoire, a gravity Remontoire, was invented in the late 16th century by the Swiss astronomer and clocker Jost Bürgi. However, the spring Remontoire is an invention of John Harrison for this marine chronometer H2, which he finished in 1739. Instead of restricting the mainspring, a Remontoire separates the escapement from the rest of the movement, isolating it from the mainspring torque variation. Instead of receiving the impulse directly from the train of wheels, the escapement interacts only with the Remontoire. The Remontoire itself is a spiral spring which is periodically rewound by the mainspring. As long as the mainspring has enough torque, the Remontoire will provide a consistent flow of force to the escapement. And so we come to the Chain-and-Fusee, where we can broadly say that the Stackfreed, Stopwork, and Remontoire function by accepting that the mainspring will deliver diminishing torque as it unwinds. The role is to alter the effect of that without ever physically improving the behavior of the mainspring itself. The Chain-and-Fusee, however, is an approach whereby the torque of the mainspring is rendered constant by actually physically improving the behavior of the mainspring. And it does this by employing a mechanical principle, the principle of levers. We can see the fusee in concept in the notebook sketches of Leonardo da Vinci. So it was already a no idea when horology adopted it. We can see here. The basic chain fusee is a cone-shaped pulley connected to the mainspring barrel by a chain. But when it was first introduced to watchmaking in the 15th century, it was with a core typically made from catgut. The bottom right photo is one of the earliest examples of a fusee clock completed by Jacob Zech in Prague in 1525. You can see the fusee is tall and narrow. It used catgut instead of a chain to connect the mainspring barrel, while the catgut has not lasted over the centuries. So you can see here there is the fusee, but the catgut is missing. Here is a movement of a pocket watch from 1880 that employs a fusee and chain with metal links. So the metal links that are very small, but you can see over there. Instead of the barrel directly pushing the gear train, it works in concert with the chain fusee. And it's actually the fusee output gear that pushes the gear train. You can see that when the mainspring is fully wound, the chain is wrapped all the way to the top of the fusee, where the radius is the smallest. Why this? The compensation is quite simple. I always say that it's simple, but when you have to take a door, you know, the mechanism is never at the inside of the rotation, but is always at the outside of the door. So this is exactly the same principle. If you want to compensate more, you use a big radius. If you want to compensate less, you use a small radius. This is how simply we can say it's working. As the mainspring unwinds, the barrel and fusee rotate and the chain is pulled onto the barrel. The chain unwinds from the top of the fusee to the bottom in an increasing radius so that when the mainspring torque is at its weakest, it is applied to the fusee widest radius. If the chain and fusee are designed and produced correctly, the mainspring and barrel, this allows the torque provided by the fusee to remain constant. But why does pulling on the fusee and its smallest radius compensate for the fully wound mainspring? And why does pulling on its largest radius require less force? To understand, I want to take you on a bicycle ride along the Col du Marcheru, near my home in the Vallée de Joux. When I'm cycling along on the flat ground or even going downhill, I can put my bicycle into a high gear in order to pick up speed. When I arrive at the hill, as often do on the Col du Marcheru, the gradient is steered until to 14%. I lower the gear and the derailleur shift the chain to a sprocket that is larger in diameters, allowing me to rotate the rear wheel of the bicycle with the same energy. Without the gear sprockets on the back, I would like to increase my energy to maintain the same speed. But the gears allow me to provide the same energy to maintain the same speed. So in a watch movement, the energy is not like a bike rider. The energy is always diminishing. And this way is why without the fusee, similar to the sprocket on the bike, the torque delivered to the movement will not be able to maintain the same precision. Indeed, Alanger and Son describe the chain and fusee as an infinitely variable gearbox. And I think that sums it up quite well. After the first fusees made their appearance in clocks in the 15th centuries, timepieces began to shrink. By the 16th centuries, you could fit an horological movement on top on your table instead of a clock tower. And by the 17th century, you could fit a timepiece in your wrist, and the vast majority of watches and clock tables included fusee chain mechanism. Being able to provide constant torque without needing to keep a timepiece stationary meant that probability became a realistic goal for watchmakers and a fascinating one too. While the chain fusee design solved the problem that had perturbed watchmakers for 100 years, there was no escaping the fact that it took a lot of space in a watch, meaning that pocket watches of the time were quite large. By the end of the 19th century, the fusee chain expenses and difficulties watchmakers had in maintaining or repairing it led to its almost total abandonment. We can see here the type of chain, a lot of part of the part missing, and me when I go in Switzerland to see different places and like a small, I can say, auction or thing like this, we quite often see that type of movement doesn't work because there is a lot of problem with chain and the different parts. There is one notable exception. We kept the fusee chain in operation until well into the 20th century, the marine chronometers. Life at sea presents many problems for clocks, and their spring in particular. We're talking about large variations in temperatures and humidity, in addition to the constant, unpredictable movement of the ship. That's a lot of variation, and remember, the chronometer is behind used to calculate the ship's position. So the timekeeping accuracy of the marine chronometer was integral to the ship safety. Plus, the generous size of the marine chronometer compared to a pocket or wristwatch meant the generous proportion of a chain and fusee mechanism could be more easily accommodated. So the chain fusee was still used in marine chronometer until about half a century ago. In this country, for example, you had the Hamilton Model 21 marine chronometer produced after a 1939 request from the US Naval Observatory. In more recent times, the Chain-and-Fusee has seen a return to use contemporary haute horlogerie. A Lange & Söhne was the first up to downsize and traditional chain and fusee mechanism to fit in a wristwatch. The Tourbillon pour le Mérite in 1994. It was an important timepiece and one that coincided with, or indeed helped fuel the modern-day renaissance of complicated mechanical wristwatch. On a personal level, I was very happy to discover that the Pour le Mérite collection by Lange. It confirmed to this mechanical principle had a place in modern days in watchmaking and not just in the 15th century. So now I will start to be a bit less concentrated on what it was for me the past, and I choose to have some line and to be precise about the past. Now I will be a bit more relaxed, and I will talk about some of you also are waiting for to know about why I developed a constant torque. Why was my thinking, I can say, behind that. So the first watches that, the first caliber that I did was with the Prestige HM. HM at that time, I had to be very conservative. Conservative for what? You know that my background is about precision mechanic, and after that engineers about machinery. So I had also to learn about how it works. How work a simple mechanism. And the reason it was for me, Romain, you have to know to walk before to run. So it does mean in watchmaking, you have to know to build the most simplest movement ever, an hour, minute. Then after that, maybe you could imagine to be differently crazy, but at least you have to start with that. So at that time, when it was for me the first time to present at Baselworld in 2007, it was, for me, also very challenging. It was already at that time that the complication, the extraordinary timepiece was already on the way. So it has been just to arrive with a simple movement. It was also a challenge for me. So the collector started to appreciate us by the finishing, and it's how everything started. So I slowly understood that most of the time, a lot of journalists and collectors and all of that, we talk about precision. But precision is something a bit more technical than what we can expect. I understood after calibers and calibers and calibers, in different point of view about where was the difficulty. And the difficulty was exactly, as you can see with a regular curve of precision, a regular curve down of amplitude, that nothing is stable. And that one, if you take at 24 hours, has a precision like very, very precise. Here you can see the result of all of this, which is after 48 hours, you see 4.5 seconds a day with a delta of 4.8. But when you look at the graph, it's like, oh my God, what it is. But this is exactly how a spring, if you don't operate and you don't wind it frequently, you will understand that the precision of your watch will be affected. So physically, I understood, and I was thinking about Romain, how can we speak about precision if we don't talk about when? And the question was exactly that. In physics, we will say, what is the precision of your watch at 10, T10? What is the precision of your watch at T24? What is the precision of your watch at T40? This will be the right question, but not just only what is the precision of your watch. And this gave me, and from the mechanical side, by the thinking about Romain, no machinery works like this. Why we ask for that type of mechanism to be constant if we never deliver a constant energy before? So this was exactly all of my thinking behind the concept about a constant torque. It was to deliver at the mechanism a constant input if you want to obtain a constant output. So here we already saw when it's fully unwound, when it's fully wound, this is the curve of the power. So here was exactly, like I said, the precision at 24 was very good, but we understand that everything goes down in terms of amplitude. The traditional chain-and-fusee was, for me, very interesting. And at that point, for me, I really started to consider and to understand about that mechanism. That mechanism for me was the only one, like I said, to really compensate physically something. And here we can see, for example, the different problems that it was. The numbers of layers that you had to enroll. The chain was enrolled with the barrel. And the length of the chain was obviously a problem. So when I was thinking about to go with the constant torque, I clearly understood, and I saw so many old pocket watches that they are just, we can say, unfortunately out of order. They are just dead because the chain is rust, the chain is broke, and how to doing that? It's really difficult to service a chain from the 17th centuries or for the 18th. So I was thinking about Romain. The idea is excellent, but the problem is probably the chain. And your collectors will be sensitive probably if you produce a chain as everybody done before. So I had a complete rethinking about the constant torque mechanism and the fusee, and I said to myself, Romain, you have to think about how to change the chain. The answer for me was quite easy because from the mechanical side and the bicycling, I already knew how was a chain before. And a chain before, in terms of motorcycle, bicycling, everybody knows that it's always 2 links outside, 2 links inside, 2 links outside, 2 links inside, which is not the same way as the watchmaking. The watchmaking has a big problem. You can understand that if you have to enroll multi-times here, 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 your chain cannot be very thick. So they had to find a way how to save the space. We already say that it was a problem about space. So this was the question about how to do. And the result was the thickness of the chain with 2 links and 1 link. So now it's easy to understand how we can say and imagine, you know, certain security if in some part you have 2 links and another part 1. And it wasn't like 2 links and a bigger link. No, it was always links at the same thickness. So by that point, I said, Romain, good. You will do the chain differently. It's going to be more mechanical. You can take more space. And also think about one point that we can see here. It's always affecting the barrel when the chain is going to be unrolled and to touch. We will see later some pictures about, we see clearly some mark on the barrel. So I was thinking, Romain, to avoid the friction, because the mechanism will be different, that's maybe the time to think like the bicycle chain. The bicycle chain has roller inside. And the roller is made because the chain is moving, and when it's touching the gear, the roller can adapt much more easily than just a link. A link, in terms of friction, will do that, and the roller will adapt slowly. So we are going to reduce the friction. So a bicycle chain without the roller, it will be never good with a good efficiency. So I also understood that here that's the different drawings for the patent. And when I designed the first chain, I didn't imagine about one point. I never realized that it will be complicated also regarding the chain. Because I discovered that the chain is a rubber, is an elastic. So depending about the mechanism that you have, the strength of the chain and every link, there is no importance. You will never see that, but the chain will do that. So due to the mechanism that you will see later, we had to do a lot of mathematics, help with computers, to really see where are the strengths and how to reduce this as elasticity. And we had to do until 7th prototype to obtain the best links who will try to almost don't create this problem of elastic. So you can imagine if you have 20 links or if you have 100 links, you just multiply the problem on every link. So the chain that I developed is with only 136 parts, which is fundamentally different than what we can sometimes read in marketing. My thinking was for the collectors. My thinking was to say, Romain, you have to reduce the length of the chain because so much links you have, so much problem you can have at the end. So the idea about that was really focused for the collectors. It wasn't focused in terms of marketing to say the huge quantity of parts, but it was really to think about the future. The difference was also in terms of assembly. As you can see here, on the patent, there is a rivet. So in 50 years, if something happened, or in 100 years, if something happened and I will never be here, any watchmaker will understand that he can take out the rivet here. He can take out all of the axle here, reduce the length of the chain, and fix again. This is only going to affect the power reserve. That's it. But the chain is going to continue, which is something also in the pattern and all of the thinking. I was thinking about that, how to after-sell a chain. And all of the principle was made with that. So you see the length of the chain, 3.5 millimeters, instead of very long, more than 20 centimeters of chain. But the marketing are happy with that. Here, one of our watchmaker to see the dimension, the thickness. So not very big. Like I said, two links inside, the rollers in ruby. Also the same thinking. We never do in watchmaking steel on steel. It's why every pinion will rotate and has a function. We use the jewels to preserve and to reduce the friction and to grow the efficiency. One of the problems in watchmaking is about to avoid to lose too much energy. So if we reduce the friction in every places, it saves the quantity of energy that we need at the starting. Then after that became, and at the same time, how to do that, how to not enroll so many times. For me, I can say it was quite evident in the thinking about the fusee is a colimaçon, you see, like here, and going inside. And I said, if you press in one layer the fusee, and you join the highest point here until the smallest radius of the fusee, it became a snail cam. And it's how gave me the possibility and the thinking about Romain. This is a principle that you can use exactly the same. It does mean the difference of the radius that I have here from the center and here from the center will exactly do the same as the fusee. So now I will show you and explain a bit more how it works. This is, I'm not going to say again, you understood about the power, and the maximum power goes down to 0. So what we do is, here we don't see very well, but we cut that part. Firstly, you remember the Stopwork did exactly the same. So it has meant to cut here, then we also cut that part. Okay? Difference after that is, that was the question. How to compensate the losing of this energy here that we see with a mechanical principle. The answer was that. How and why the fusee we had to do that? It's very simple. It's impossible to compensate the infinite. This is why, in a way, you have to shorten the power reserve of the watch. And this is why you don't see a fusee chain with 100 hours of power reserve. It's 36 hours, it's 45 hours, it's sometimes 50 hours, or it's 46 hours. But as you remember, the first graph that I show you, no, this will be later. It's another one. It's impossible, like I say, to compensate the infinite. So the part that we have to compensate is here. Now, how it works. There is no mathematical solutions because it's related to the mainspring. So at that time, it was complicated for them to doing a precise fusee. And this is why sometimes you see different kind of shape. But this has to be always related with that line that you see here, which is the energy, the torque delivered by the mainspring. So if you think about the point 1, like I said, this is the place that we have the less energy. So this is the place that we have the biggest radius. The point 2 is the place here that we start to have a smaller radius. The point 3, same, smaller radius. Point 4, same. Point 5, same. Same with the fusee. It started with the 1 to 5 by the differences of the radius. So today it's quite easy for us because we can have those kind of tests. So the report about the springs, and after that we can really correlate the shape that the fusee has to get. But without, this is impossible if you don't have the spring. So anyway, you have to doing all of the engineering, all of the calculation before to do the fusee or the snail cam. You have to do and to calculate everything to get that part. And we compensate only this. So now, is it really working? That's really a question that we think about. And now I will show you something that I never show for nobody, and different things after that also in the different graphic here. Things happened that I was not believing. How could we do a watch with more amplitude at the end of 62 hours than at the starting? Here you have. From 0 hours, after 63 hours, I got more amplitude. And you see the precision of the watch? So this was a mistake, because I compensate just too much. But this just proved me, like we say in geometry, it was what it was necessary to prove. So this mistake, this error, proved me that, Romain, the physical principle work. And I was very happy about that. And then after that, I compensate by another way and get something with the same amplitude almost. The precision, you can see, is flat. So I have shown that kind of graph to big companies. And I remember 3 weeks ago, it's not too old, with a very big company with a lot of knowledge in terms of hairspring and all of that. And the question was, is it almost working, the constant torque? It was like an ironic question. And okay, I didn't take care about that, and we did the visit and the different things. And then after that, I showed to them that kind of thing. And they were really impressed, because if you have something like this, you see the result here. And this piece is the first piece that we deliver to Cellini, the yellow gold edition number 00. Average after 44 hours, or some, I don't read well, 44 hours, 0.1. Delta of position, 1.9. Yeah. So here we can talk about precision. And you understand that if you have the precision of the watch here, 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 or here, we can talk about precision. And you don't have to specify fully wind, half wind, where. No, at any time. At any time, the watch will remain the same precision. This is logical. So it was also for me, an enormous challenge to think about that. A complicated mechanism and a fusee, if you don't place this in a design way, it's going to be already complicated for everybody to understand about what it is. So the logical one, you see the secondary barrel, the snail cam here, and the back with a lot of things. There is a lot of things to explain, but now I think a lot of people think about how it works, because it's completely different than a fusee. And the principle is different. The fusee do 5, 6, 7 turns, So that means here, my difficulties was to say the snail cam here cannot turn more than 300 degrees. So how to do? I will ask you a question. In a watch, who gives the power reserve? Who gives the numbers of hours that it's possible? It's always the barrel. It's always the spring. How it works with logical one? The barrel here, that you see very well here, we use only to deliver torque. Only that. We don't use the barrel for the power reserve. This is why, if you remember the that graph. Here it was 63 hours. Then after that, I went down to 43 hours, to 46 hours of power reserve. So how it worked? I had to demultiplicate by a reduction gear the numbers of turns of the barrel. Then you arrive to the secondary barrel here, and you goes up by the chain to the snail cam. And now, the difference is in a normal watch, in a regular watch, this is the barrel who gives the energy at the center pinion. And all of the mathematics of the movement start at this point. So I had to regenerate the number of turns of the barrel by the multiplication gear train that you see in green. So this is the part here and the part here. So in a way to reduce, and another way to grow again the numbers of turns until where? Until the center pinion, which is here. And another thing's a bit different or logical. Due to the mechanism and the complexity, it was almost impossible to wind it like a regular fusee. So I had to think about another way. And the other way was about a push winding. And the push winding is probably today, and if it's not, we are never sure, but it's the only one watch on the market to have a push winding. This is an enormous quantities of parts moving in 1 millimeters. So in 1 millimeters of push, you have around 50 parts, mechanical parts moving in 3 levels. One is about to turn the barrel. The second is about to give energy in that part. And the third level is to turn the snail cam and the chain. So how to do that? By just turning a crown. It will be very challenging and difficult. So this is why the push winding came. A lot of different things in the principle about how to transmit the constant torque. I had also a thinking about the attachment of the chain. Before, it was on the barrel, it was like a hole, a linear hole that you can fix one link, and all of the power was applied by this. I was thinking about that's not really the right way to doing. Let's doing and using really a way by a bit more mechanical. As you see here, the attachment is with 2 links and the axle. So it does mean the power is really transmit with a linear way. And this was also one of the thinking. Everybody knows that normally the chain, they are not developed to get torsion. They prefer to work in a linear thinking. And this is why also, in addition of all of the problems about the length of the chain, the thickness, the way to avoid strength that the chain is not fit for was really, for me, important. And here you can see all of the mechanism work in one layer, so in one line. So the barrel here with a different conception, you see how here we take care and how the strength is transmitted with the secondary barrel. Then an interesting point about the strut bar. I like sport car. I like cars since a long time, and from that mechanical approach, I also learned about with cars that when you have the motor and a lot of stress to manage, they placed the strut bar to rigidify. So the meaning about was exactly that. The meaning of this bar is like the sport car to be extremely rigid between the 2 important points. Then, for sure, different problems are also in terms of manufacturing. Today, we We have 500 only dedicated for manufacturing. This is a part of my background about to manufacture pinions, wheels, cage of tourbillons, and all of that kind of point. We know well about titanium, and this is the reason why I decided about that part to do in titanium. If it will be, for example, in steel, it will be complicated with the heating treatment. It does mean the part will, with the tension inside the metal, will twist on curve a little bit like this. So I said that will be anyway at the end a problem in terms of manufacturing. So let's use the titanium. Here is a titanium grade 5 to get the polishing on every side. So much more complicated for the finishing, for everything, but the titanium grade 5, I didn't have to do any heating treatment. So it does mean from manufacturing with the perfect design, the perfect precision, it will be never affected behind with another point. Then after that, different way of watchmaking. We can have a look here on the dial, enamel dial, and what is logical one at the end. So I think now that will be the different source, the moment to thank you and questions.
So before we get into general questions, it would be a disservice to our lecturer if I didn't mention that he was one of 31 members of the AHCI, which is the Académie Horlogerie des Créateurs Indépendants. And this is a very small and exclusive club. They just recently celebrated their 25th anniversary, and so I'm going to take my privilege as the host this evening to ask what sets you apart from the other members of the AHCI.
Yeah. If you just can, I didn't really understood about the...
Oh, so you were AHCI?
No, I'm not.
Oh.
No, but it's not a problem. No, I can talk about the point. You know, the AHCI is reserved for the watchmaker. Oh, I'm not. So this is why I can understand about maybe I can say the confusion, and this is normal because a lot of people are thinking about that. But well, I guess, you know, watchmaking is a big area. If you think about today, who developed the movement, the calibers in the big companies, they are not watchmakers. They are engineers. They come from the mechanical side, the micro-mechanical side. So it does mean it's why, for me, when I started watchmaking, it wasn't a problem. You know, today, Philippe Dufour always say for me, Romain, stop to say that you are not a watchmaker. You are a watchmaker. But basically not, I'm not a watchmaker. And I was thinking about, like in the past, you know, it was the people, the watchmaker, or the person with ability with hands who was developing, who was manufacturing every single part to understand where is the difficulty. Where is the difficulty to machining a wheel at 0.1 millimeters of thickness instead of 0.2? Me, I know. But if you never machining parts, how you will take care about that? How you will understand? I can say for you, we also did parts for different brands that the machining was 4 hours and a half. So it has been those things very complex that we were the only one in Switzerland to be able to produce. And manufacturing is really one of the key. I always say if I started with watchmaking, probably I will not be like that. How to be a manufacturer? If you learn watchmaking, you don't learn how to produce. Today, I can say this is disappointing, but that's the reality in watchmaking, that the watchmaker touch less and less machinery to machining parts. Because the reality of watchmaking today is that we provide, the mechanical side provide to the watchmaker the parts. And most of the time, and always, the parts are also always finished. So the side of the watchmaker is to set up, is to assembly, is to regulate, is to doing all of this thing properly with the oil and all of that knowledge. But there is an enormous quantity of knowledge behind that. When we have visits, when we have groups, or when we have collectors and journalists, I spend 2 hours in manufacturing. After 2 hours, they are like, yeah, because unfortunately, most of the brand, they stop to explain about that. But if you think about that's the place in watchmaking where we need the most knowledge and that we have to do the most investment. A lot of people are thinking about CNC machinery is like it's too easy to do that. Until Philippe Dufour, a few months ago, he did the visit with a small group, and also the eyes of Philippe Dufour was like this, because he understood that behind a numerical machinery, the machinery does nothing in place of doing movement. Just movement. The machinery don't know. If you have fixed tools with a square shape, with a triangular shape, with a banana fixed in place of the tools, the machinery are just going a jam of banana and stop. Like this, if you want to work like forever the machinery without any tools, the machinery will do that. So it has been behind all of those machinery. You need technicians, engineers who are able to design the tools, who are able to know about the metal, to know about the precision, to know about everything. And precision is also a question of temperature. So the knowledge is really, really enormous. And the challenge today for most of the companies is not to engineer, but how to produce those very, very small parts. And always, like, for example, I have visit again, I showed one of the smallest part, which is the anchor axle in every watches, okay? And it's funny because we have a space like this with multiple space, and in one block, I have just one single axle anchor. Normally, nobody see the part. So they are like, and when I place under the microscope, they understand. They understand where is the space for the hands and where is the space and the advantage that we have today about machineries. The complex watches that you see today will never ever exist without the type of machinery that we have. What is the difference than before? Because before they did incredibly complicated things. And now, you know, I started, so I can talk with you for hours about that. So after that, it's you about questions. But the point is really about how they did it before. They had time. That today, nobody take the time anymore. So when you have time, anyway, if you need 1 week to achieve a cage of tourbillon, like you probably know at this 200 years ago, it was like extremely thin, like almost unbelievable to understand how it was made. And with time. Today we have machinery we can do by different way, but never forget that the quest of reliability, the quest of precision is also related to the type of tools, equipments, and technology that we have today. I always say if Abraham Louis Breguet will be alive, if Patek will be alive, if Audemars will be alive, they will use our machinery. Since the starting watchmaker don't do everything with the file, they started to develop machineries. You all know the beautiful machinery with the stand in wood and the beautiful brass wheel and all of that. It was already machinery. Unfortunately, they had to turn with a human motor But today, everything is by a different aspect. But how to manage all of this? It's not easy at all. And yeah, but it's why, I never asked the HCI to be member. And also in respect of the watchmaker, I'm not, but I'm born in the right place. And I saw all of my life watches. And when I started to think about that, my vision was about, Romain, a movement is a small machine. So maybe you can do it.
Well, now that I've nominated you.
Thank you so much.
Yes, you're welcome. I'd like to open the floor up to questions, please.
Okay, I'll start. First of all, that was a absolutely wonderful and very technical lecture, so thank you for that. So you mentioned that if Breguet was alive, he would be using and taking advantage of CNC machines today. Do you think that Breguet would also be using silicon nanofabrication technologies?
Difficult to be in the place of Abraham Louis Breguet, but I could say yes, in a way, because if you are looking for creativity, you are excited by the new things. And you never close your eyes about new things. You have to consider about new things. Anyway, if sometimes we have, and it's always the case, in my case, I prefer to be conservative, to go slowly and this. But at that time, it wasn't really a question of competition. It was a question of knowledge, competence, and skills. So it has been, for sure, but the things will be crazy if you imagine what they did before and what kind of technology, what kind of knowledge in terms of metal, physics, in every area, in every space that we have today. I think it's why, I decided to think about the evolution of tradition as us, and to think out of the box, not to just copy the past. And this is related also, I remember 10 years ago, the journalist was always asking me about, Romain, what do you think about Chinese, about China? It was always the question, and it was always, for me, a disappointing question. And I always said about, China doesn't have the same culture. They follow well, but they are not necessarily the pioneer. So it has mean they just copied the Swiss, okay. But what the Swiss industry mainly does, they copy the past. And this for me was something that I said, Romain, your space is not to doing as everybody. So try to be innovative, try to be creative. And for that, it's an another challenge. It's an another thinking. And for me, to explain the differences, and it's important, I have a huge respect for brands because, like, for example, Rolex, for every brand. And the thinking about what advantage when we are like us, with an independent thinking we have. When I have to develop something, when I have to design something, I never compromise. But I never compromise because our clients are not waiting for compromise. They are waiting for something exclusive that was probably never made before. But where is the difficulties for the brands? For the designer and engineers in major brands, they have a target in terms of price to achieve. They have a target in terms of quantities to achieve, which are going to affect the design, which are going to affect the engineering. Who will take the risk? Who will say, yes, we go, yes, or not? I always say the logical one should be developed by a major company. That will be complicated because how to mix the design and the engineering with two teams who will fight to say, no, a bit more here on the left, a bit more here. But no, we cannot, you understand, a wheel has teeth. We cannot stretch it, so it has to be here. So then after that, it goes to the board, you know, to the level, the upper level, to explain about who will win, who will have advantage, the designer or the engineer. Hopefully in my head it was the engineer was me, the designer was me, and the board was me. So much more easy to take decision, but also easiest to take risk. And I know that for everybody to take risk is complicated, but this is what we have to do, and this is how we can achieve that. It's because we have few brands like us, the liberty to never compromise and to go in a level that if you want to taking part about the concurrence, you cannot do that.
Thank you. Just a mechanical question. It looked from the old fusee and chain that over the course of the moving the chain would actually move, right, from one position around the fusee to around the barrel. But in your logical one, the chain is short, so it does not look like it moves fully away from the fusee at the bottom over the course of the watch moving. When you press the push button, does the chain actually reload and it's moving through the course of the day?
Yeah. When you press the button, is here. So it does mean here we can see an arbor, here we see a finger. We can say we'll turn this small gear here, and that will activate this. So on every push, you gain around 40 minutes of power reserve. And on every push, this is the only one time that you will see all of that part moving is at the pushing time. So on every push this is going to slowly do this. One push more, one push more, one push more. And then after that, slowly, the power, the torque is going to be released. Yeah. So don't hesitate, like I always say, it's also easiest when I do some visit, that I can answer about everything, you know, from marketing, business point of view, strategical point, mechanical, engineering, design. So don't hesitate, no, maybe not just only about the constant torque. If you have other questions, that will be my pleasure.
Thank you very much for the lecture. It was really fantastic, especially for the watchmakers and the technically inclined amongst us. I was wondering if you had ever applied any of your creativity to mechanisms to the escapement, thinking about making practical improvements to the lever escapement.
Mm-hmm. Absolutely. You know, the difficulties today is that I had so many ideas around 2009, 2010, 2011, and including complications that I just placed under the desk because I had no time anymore to think about that. And, you know, after that, I had to build a team from myself to 25 person to be a manufacturer. This took me more than 10 years, you know, to achieve that. So it does mean now I will go back. I come back slowly to the development. I go to the manufacturer in the morning. In the afternoon, I can stay at home and be creative and be in my bubble. At that time, I had a huge thinking about that, because if we think about the efficiency, about the escapement, we can say almost every escapement, it's always, I can talk about that, but it's a part of my vision about why. It shouldn't be like that. It's always a problem about start, stop. Start, stop. Release and release. Release and release. Here we wait a lot of energy. So the Swiss anchor is 30% of efficiency or something like this. So for sure, we we can develop different things. And this is why, for example, the Girard-Perregaux, the different kind of system like this, I like that. Yeah, I think it's the 21st centuries, you know, about that kind of point, the silicon, the different possibilities. But it's for me, it's two way of thinking. 21st centuries for one, and another one a bit more conservative. My background is about precision mechanic. I like machining. So when I develop things in that sense. But for sure, the new technologies today push the limits in another level. So it's why the performance apparently about the Girard-Perregaux is quite incredible. But this is because they reduced the needs and the friction, and using the the wafer and another technology to produce very, very, very thin springs. Exactly. So there is a different approach, but for me, for sure, my thinking, and I have a mechanism in my mind, but this needs test, R&D, money, and to investigate, to think about that, to take risk, and maybe for nothing. So for me, it wasn't the time really to think about that. Maybe a day I will come back in my vision about, but I totally agree that we try to fight with something at the end with a non-efficiency, yeah, which is almost every escapement.
Hello. You mentioned about the Stackfreed and that type of mechanism didn't last very long. What was it about that mechanism that was inefficient?
Good question. Yeah. Here we have the answer. When I saw the picture, I was not surprised at all about what you can see on the picture. Have a look on the spring. Here there is a kind of roller. Do you see how this cam is totally damaged? We cannot say by another word. It's absolutely damaged. So this is going to change, you know, to create a lot of problems. So providing a system by creating friction, additional friction, is exactly the opposite that what we need in a watch. And this is how they compensate by doing a bigger spring, because so much friction was related here. And the efficiency of a watch, for example, for you to understand, the best movement will be with the less power in the mainspring. Because with all of this, we have a lot of pressure on the pivot of the pinion. And when we develop, we have to calculate the pressure on the pivot. So it has been more and more simply for you to understand. I'm going to take a picture about, yeah, we can take that one. You know, the maximum power always starts from the barrel. Then after that, you have the center until the escapement wheel and the balance here. So why we reduce the diameter of the pinion and why the axle balance anchor are so small? Because we have less and less energy. The biggest torque and energy is here, but then after that here less and less. So it has mean the problem of friction is the reality, and more when bigger the spring here is, more pressure we have on the pivot and more friction, and that means the lifetime of the pinion and the watch is going to be affected. So the perfect watch will be like the smallest spring here, and this is going to go in a vision about, yeah, a year of power reserve or something like this in the same space. We could maybe a day achieve that kind of things. There is longer with 31 days. I guess there is more today, but it's multiple barrel. For example, if you read the theory about how to build a barrel, it's always mentioned about that you should never engineer a barrel more than 8 or 12 turns. And this is what I like in terms of watchmaking. If you see the longer 31, it's not just 8 turns, it's not just 12 turns, it's a lot of turns to obtain 31 days. But they did it. So sometimes if you just read the book, if you just apply the engineering principle, we never push the doors of new ideas and new possibilities. And this is like in the past, it was also the theory from the crown position where the balance has to be. Today, I think all of that kind of principle are probably different, yeah.
Two quick questions. One,
Yeah.
That is a back wind,
Yep.
and the other that you showed us later on is the push wind.
Yep.
Can you explain the evolution in terms of how you got from that to the next one? And I don't know if this is personal or how many pieces do you produce a year?
Absolutely. Okay, so with the last question, today is going to be hopefully 65. Yes, it's going to be that. And this for you to understand why 65 and why only that quantities. Because it's not necessarily related with the watchmakers. The way that we do has an enormous amount of beveling. But the beveling that we call that by the file, which is not the same type of beveling that the Geneva seals, for example, accept, which is with a wood turning that you come and the friction of the wood with the bridge start to polish and doing that. There is a huge difference. It's also a thing that I explain very well when we have visit, but it's like if you compare 3 minutes on process versus more than 20 hours of some bridges of logical one. So how you can compare? There is a huge difference, but the difference is not, there is a huge misunderstanding today and a big mess in terms of hand finishing. The polishing is not the point to be shiny. The hand is, yes, it's good for that, but it's like if you have to polish that by hand, you know, it's round. In addition, it's a shape that you will say, why you need me to do that? No, you can use a machinery to polish simple things like this. So the beauty when you use human and person behind is to change the shape. It's like the furniture, the Louis XV in the past. It wasn't made by machinery. You see the shape of there is a lot of sharp and beautiful artistic shape and lines. And today I can say it's really depending about what is your goal. But me, this helps me. I will go back now to logical, because the question from, I can say in terms of design, it started already, you know, with the sharp angular, with the internal sharp angular, all of that kind of things. We need the hands of a people, of a human. Then after that, with logical one, it was a bit more complex. How to finish that kind of bridge with 2 layers, with 2 small arms. The needs was for me, Romain, if you have a top of the watch with an open dial, has to be as beautiful as you can have normally a normal dial. So the needs of the bridge was to be the most beautiful as possible. And the most beautiful as possible is not with machinery, is with hands. And that bridge is more than 20 hours of finishing in one, which is impossible to replicate. So why 65? It's because today we have 5 persons, there will be 6, just for beveling. And when it takes for a logical one, for the best, the head of beveling, she takes around 80, 90 hours to do a kit. So that means all of the bridges of logical one and the main plate, only that takes 80, 90 hours. When it's a person with less training, is over than 100 hours. So you can imagine, you can replicate the numbers and all of that with different quantities. I will never, ever be able to produce 500 watches with that level of design. Not just that level of finishing, that level of design. That's the key. But this is when you do the right reverse. Human, made for complexity. So I can change the design? Yes, you can change the design. You don't fit just with that because you can say it's hand finish. That's for me for sure, it's finished. But if we use human, it's going to be for complexity and for shape with more difficulties. So from the Prestige HM, for me the thinking was already with an engineering point of view. Why to always reverse the winding when the watch work always like this? And I was thinking if you place the winding with the same, you don't have to reverse any mechanism. So it's how everything started, but not just by that way. When I said to myself, it's nice to have a crown on the backside, but that will be a pity if you have to take out the watch to wind it. This is why the position of the crown is here, and this is why you have a small access to the crown. This, when you wear the watch, you can wind it. And this was really at the starting of the engineering. I didn't have that thinking after. The good importance is to think about your collectors. Who will use? What they are going to like or dislike. And this was for me really important to think about the position of the crown. And after that, to have an integrated crown that nobody can feel, and to have another thinking about winding. But all of that was made because the HM has a perfect balance everywhere. So it doesn't matter in a way if you were on left or on right. And I really liked that by the point of the design, to don't hurt with a crown. Then after that, I started to continue. I don't like the crown for me at 3 o'clock. This is why here you have a small crown on logical one. Almost you don't see, but the small crown is here, because that crown is only made to set up the time. So when I was a bit more crazy at that time, and when I developed, I designed with a sapphire crown to delete the perception of the crown. But unfortunately, the sapphire was a little bit too sleep. Exactly. So okay, it wasn't the right idea, but I keep, the same vision about I don't like to see crown. And this is why, also the principle and the difficulty is just to turn a crown to wind a logical one with around 50 pounds to move. When I was thinking about the push, I said, that will be another way and also discrete and different, so let's work on the push winding.
Romain, the one slide that stuck out to me as the most impressive. The other slides, you have many chains, and the chains often have kinks in them. And anybody who's worked on a bicycle, you pick up the chain has kinks in it. You've got a slide with one of your finishers who's holding up the chain, and it falls absolutely dead straight down. That last one you just had.
That one?
How many chains did you go through to get one that fell that beautifully?
No, today the watchmaker, they have quite a lot of skills to do that, but but for sure, you know, they don't fix it like this. We have a holder to be precise and to maintain about that. So it's why it's not like we, you know, like a freestyler like this. It was more for the picture. But for sure, we have some order to maintain the parts at the right position, and then after that to apply. But it takes, for a watchmaker, you know, it's only 136. Sometimes I have read more than 800 parts to assembly. But 136, you know, it's here, so it's 28 pin like this, and we can say for a watchmaker, it takes around 1 hour to assemble one chain. So it's why, you know, to doing a service, it will be not a big problem. Yeah, but all of the techniques, all of the things different is related with the sandwich that you see here. Everything has to be perfectly precise. So, like in the past, they were assembly with some small slice of very thin paper. Then after that, when they did the assembly by stamping, then after that they burn the paper to get some liberty, some freeness. Here, it's absolutely not the same. It's the tolerance of microns on every side, everywhere, who gives the freeness. So it's another approach, much more mechanical than it was in the past. And they did in the past, they could do that, I'm sure. They probably had a thinking about that. But how to enroll 6 times, 7 times, 5 times a chain like this? It will be never possible. So this is why they had to compromise, probably, and to say about, okay, the chain has to be very thin. How to do that? And it's why they didn't have any head, any rivet, but it was by stamping.
So as is tradition, our guest often stays for a few minutes after the close of the meeting for additional questions if anybody else would like to come up and ask in person. With that, I would like to please let everybody know that our next meeting will be December 3rd. Our guest will be Andreas Strehler, owner of Urteil AG from Zurich. The topic, Tradition and Innovation, a Contradiction. So with that, please, a large round of applause for our guest. Thank you all for coming, and I look forward to seeing you again soon.